Okay, yeah. Okay, since I'm also one of the organizers, so I can't thank myself, but let me just thank this other organizers, also, especially Hugo, for initially proposing that we have this program here, and I think it's going on quite nicely. Okay, so this is the title of my talk. So all these keywords in different colors, and as we go along, I hope it will be clear. And so I know that, okay, many of you may not care about what is the fluctuation theorem or entropy production, but since a large deviation work, so there are some, so it will be basically mostly about large deviation function of these quantities and the singularities of large deviation functions basically, and I think there's some interesting mathematics there basically. Okay, so let me just start by showing the outline. So I'm going to give a very brief review of fluctuation theorem, which is just what is just bare minimum for this talk. And then I'm going to talk about this entropy production by partial system. I'll describe what I mean by that. So what is the question we ask? So what are the earlier studies, or some of the earlier studies, our results, and then I'm going to demonstrate with a model, and I'm going to give a general mechanism for this kind of systems, yeah. Okay, so it's a very brief review of fluctuation theorem. So you know that thermodynamics deals with large systems, and then we have these laws of thermodynamics. So we encounter this first law of thermodynamics, which says that, okay, if you add certain amount of heat into a system, plus you do some work, that's basically equal to the change in the internal energy. This is just the conservation of energy. But then soon you realize that, okay, that's not enough, so you need something else, because the classic textbook example is that although this law is satisfied, you don't see that, okay, this bottle basically absorbing this energy from the environment and just jumping by 1 meter, although this law will be perfectly fine with that. Okay, so that's when you need this second law. And second law describes this kind of phenomena which you don't see it in nature. For example, this bottle spontaneously jumping up by 1 meter. And it's given in terms of various statements. And one of the statements is by Clausius, which says that, okay, heat doesn't flow from a cold reservoir to a hot reservoir if you don't do anything else. Okay, so it also introduced this concept of entropy, which says that, okay, entropy of a isolated system is a non-decreasing quantity with time. Okay, so it also gives a arrow of time. Okay, so one of the prototypical example of entropy production is, okay, if you take a thermal conductor and you stick one side a hot bath and other side a cold bath, then the heat flows from the hot reservoir to the cold reservoir. And if you ask, okay, if a Q amount of heat flows from this reservoir to that reservoir, what is the entropy change? And this is what is the entropy change in the system. Okay, but now if you go to the smaller system, microscopic level, of course, then thermal fluctuation becomes important. So heat not only flows from the hot reservoir to the cold reservoir, so once in a while you might actually see that because of thermal fluctuation, it might actually flow from the cold reservoir to the hot reservoir. So in the macroscopic system, when this thermodynamic quantity essentially a delta function at this value, so it's given by some distribution function which has a well-defined width. Okay, and so now basically this quantity Q is now a random variable. Similarly, work, entropy, all these things become random variable, and people are interested, okay, what is the fluctuation of this variable? Okay, so this is this question which deals with this fluctuation theorem, and there are several examples where you can actually look at these fluctuations. These are all the small system and where this fluctuation becomes important. Okay, so now it's also, I mean, like over these years, it has found that, okay, one can actually define this for small systems, small stochastic systems, these quantities like heat and entropy can be meaningfully defined. And if you look at, for example, if it is given by a Langevin equation, so this is, eta is the white noise given by this bath, and you always assume that bath is in equilibrium at a given temperature. So this eta minus gamma V is kind of like a force by this thermal bath. If you multiply by its velocity, it's like a power input, and if you just integrate over time, it's just this energy inputted from the bath to this particle, and which you call it heat. So then you can define an entropy production in the bath, because bath is always at a finite temperature, fixed temperature, well-defined temperature. So that whatever the heat goes from the bath to this system, minus of that divided by temperature, that you call this the entropy production in the medium. You can also define an entropy, system entropy by, so you have a stochastic system, so you satisfy some kind of Fokker-Planck equation, and so if you look at the solution of the Fokker-Planck equation at a given time, so this is now some function of this variable. Now you can, so f is p of t is some deterministic function, it's a function, but now for along a given trajectory, this u is a random variable. So therefore, this quantity also becomes a random variable. So, and this is what you call a system entropy. Okay. So given this, you can just define this total entropy, which is just the medium entropy plus the system entropy change. And this is how you define. And now if you assume that your system is in steady state, in that case, actually, it's quite easy to show, if you just define it this particular way, that this entropy production in a given time divided by this negative of it, it satisfies this theorem. Okay, and it has been shown in various form by a lot of people, and these are some of these earlier people who have shown this basically. Okay, so this is what fluctuation theorem for me for the sake of this talk. Okay, so now I'm going to talk about fluctuation theorem for entropy production. So this is the fluctuation theorem for entropy production, where you have taken care of all degrees of freedom in the system. So this is the whole system. So you have, so when I said the all degrees of freedom, so there are two kinds of degrees of freedom. One is the degrees of freedom of the bath. So these are first degrees of freedom. So these degrees of freedom are basically is given by some temperature, so you don't care about this. So when I said that all the degrees of freedom, these are the slow degrees of freedom. Right? So you take care of all slow degrees of freedom plus the entropy production of the bath, and then this is what you get. Okay, this is what is fluctuation theorem. So now what is about the partial system? Okay, so what do I mean by a partial system? Again, imagine that, okay, you have this system A and you have this system B. So they have some coupling in between that. Okay, and then they are immersed in this bath. Bath again is the degrees of freedom of bath is basically fast degrees of freedom. So you don't care about those. So of course, if you just consider A plus B, it's like again a full system. And if you look at the total entropy production of A plus B, it satisfies fluctuation theorem, as I have shown it before. So on the other hand, if you consider only system A, it's coupled to B, but you do ignore system B. And if you define this entropy production for system A, so a priori, there is no reason that it will satisfy fluctuation theorem. You don't expect that this one will satisfy fluctuation theorem. So on the other hand, if coupling is 0 between A and B, right? So then A is like an isolated system. And you expect that, again, in that case, if the coupling is 0, then the entropy production for A will satisfy fluctuation theorem. So the question we ask, okay, so if there is a coupling between A and B, but this coupling strength goes to 0 in that limit, whether the entropy production for this partial system A would satisfy fluctuation theorem. Okay, so I hope the question is clear. So we have the system A and B, so these are coupled by some delta, and we are looking at in the limit delta going to 0, whether the entropy production of this system A satisfies fluctuation theorem. Okay, so in fact there are these experiments where from this Udo Seifert and other people. So what they do is, okay, there is this two particle paramagnetic bead, and then okay, they drive it somehow, and then they look at basically one part of the system, and you define this entropy production, and what you see is that in fact it. So okay, so let me just show you. So if you write the same formula in this log, so you see that okay, it should be alpha equal to 1. That's what fluctuation theorem will say. But what they see is that, okay, there is something slope which is not equal to 1. Okay? But what you see is that as you decrease the coupling strength, the slope alpha slowly goes towards 1. So therefore, in this case, this coupling, okay, so I think this is what you see, basically this alpha. So as you decrease your coupling, so it smoothly goes towards 1. So in the limit, basically when the coupling goes to 0, the system satisfies fluctuation theorem. Okay, so there are these other system, I mean a lot of other this thing, but in all these systems, when you take this limit delta going to 0, so that's similar to the case delta equal to 0. So therefore, delta going to 0 limit in all these cases is just a regular perturbation. And you can take delta going to 0 smoothly and you get back the result as an isolated system, delta equal to 0. So the result I'm going to present here is different from this one. So in our case, this delta going to 0 limit is not a singular perturbation limit. No, it's not a regular perturbation, it's a singular perturbation. So what I'm going to argue is that the limit delta going to 0 is not equal to delta equal to 0 in some cases. And this is what I'm going to give. I'm going to define it precisely, actually. So we are going to demonstrate it for a prototypical model where I'm going to define this entropy, what do I mean by entropy production. And also we are going to define a general mechanism, so by which this fluctuation theorem breaks down. Okay, let me just demonstrate it. So this is this example where I have this particle A and B. These are Brownian particles. And I couple them by a spring constant K. Okay, and they are in this heat bath. So now the relevant degrees of freedom is this separation between them. So this is, let's call it Y. And it's a harmonic interaction. So these are my equations of motion. So this, all the blue parts is just the Hamiltonian dynamics. And this yellow part is the dynamics due to the bath, is the Lanzava dynamic. And this FA and FB, I apply some external forces on A and B, and I'm going to assume that these external forces are stochastic external forces. So I'm going to basically put some stochastic forces on particle A and another stochastic force on particle B. Okay, so this is my model. So these etas are, of course, Gaussian white noise, and this FA also I'm going to assume to be Gaussian, and this F bar square is the strength of the, F bar is the strength of this force, and this FB, I'm going to assume two models. In one case, this FB is completely independent of FA, and in the other case, it's completely dependent on FA. Basically, one is FA and FD completely decoupled, and the other is basically they are strongly coupled. And this coupling strength, the strength between FA and FB, I'm going to define by this parameter alpha. So I have now these three parameters. So alpha defines the relative strength between the force on the particle, external force on particle A and particle B. So that's called alpha. So there is this parameter theta, which basically defines the relative strength between this A force on particle A related to this temperature. And I have this parameter delta, which is basically the dimensionless coupling strength. Yeah. No, it depends on what kind of quantity you are looking. Yeah, exactly. So depend on what kind of quantity you are looking at. So of course, if you are just interested in the dynamics of this thing, it's like an effective equilibrium system. Because you can say that, okay, it's some kind of effective temperature for the system. But if you're interested in the questions like current between A and B, or the heat current from the bath to the particle, so then it's the simplest non-equilibrium system one can think of. Right? So it depends on what kind of question you ask, basically. Yeah, pretty. They're non-thermal, yeah. This is something you just imagine that, okay, this is some charged paramagnetic this thing, and you're putting a random magnetic field from outside. Like, so these are external fields. Okay. So therefore, for the purpose of defining entropy, you cannot include it in the temperature. Okay. So these are these three parameters, basically, delta, theta, and alpha. Okay. So now how do you define partial entropy production? So this is again the same one. So I'm interested in the partial entropy production for this A. So this is this heat. I think this is unambiguous. It's just the heat from the bath to this particle A. Plus I have to define a system entropy. So system entropy, of course, one can define various way, and what I'm going to say that, okay, it's not very important how you define, but basically the way I'm going to define is that, okay, you have this full system and it has some steady state, and you integrate out the degrees of freedom of B and whatever distribution you have. So this is what you call the P steady state of A. Okay. So this is one way of defining. Okay. There is also another kind of entropy production, which we call apparent entropy production, because this is the way you will define entropy if you know what is your full system is, right? Because you actually know that you have a system A and B, which is coupling, and you are defining this entropy production for A. But suppose you are an experimentalist, you do not know that your system A is coupled to system B, right? So you are going to treat then this system A as an isolated system. That's how you are going to define your entropy. So in that case, when you define, so basically you'll use the same equation, but this equation now you can replace by this Langevin equation 1 by putting k equal to 0, because you don't know whether there's a coupling to the outside one. And this is how, so in that case, you can write down in terms of this force, external force on particle A. Okay? And similarly, so that when you do that, there's this boundary term comes, and then you can again define this system entropy. So system entropy you will basically get by just solving only this part of the equation with k equal to 0, and it will give you some steady state distribution, and you stick the steady state distribution there, and whatever is that, this is what you will get. Okay, but anyway, these two parts are not very important because these are just the boundary terms. Okay, so what is important is basically essentially this integral quantity, and you see that where this large deviation comes from actually now, because you have some integrated quantity, and you are looking at the distribution of this integrated quantity. Okay, so I'm going to basically concentrate on these integrals here. Okay, so now. So you can define this time and average entropy production. So you take any of these entropies defined here, and you divide it by the measurement time, and this is your time average entropy production. And you know that it has this large deviation principle for large t, and this fluctuation theorem, what I have defined earlier, so that's at large t, it's equivalent to this symmetry relation of this large deviation function. Okay, or in some sense, okay. So let's not call it a symmetric relation. So let's P of S and P of minus S, which will be given by this at large t. And this function I of S minus I of minus S, let's just call it F of S. So now if somebody says that fluctuation theorem satisfies, it says that this F of S is linear for all S. So I'm just going to look at now under what conditions this linearity breaks down in the limit this is going to 0. Okay. So let me just give you the results. Okay, so these are these parameters I have defined alpha, theta and alpha in the previous one. So let me again remind you. So delta parameter goes away because delta parameter you can just think of it something along this direction, but I'm looking at in the limit delta going to 0. So therefore this in the alpha theta plane, see this alpha is the relative strength between force on the particle A and particle B, and theta is the relative strength between the force on particle A and the temperature. So these are my distances. So you have these different regimes, and these four depending on, okay, this I had two choices of these forces. One is they are completely decoupled and one is they are distinct. So these are these two choices, and this way these are these two choices. One is this partial entropy production I have defined by this definition 1, and this other one is this apparent entropy production which was given this definition 2. So I'm going to describe later, and it will be clear what are these symbols P1, P2, P3 are. But at this point, what I'm going to say is that if you look at this yellow regime, so in this regime, this is always satisfied, because if I look at this function f of s, it is equal to s. But in all the other regimes, it's not equal to s. Okay, it will be something else. Okay, and it will be clear why it's so. Okay, so, yeah. So in fact, one can. So this is to just convince you that, okay, these results are correct because you can actually, these lines are from the analytics, solving this thing, and these points are simulation. And you see that actually this matches perfectly. And there are these 9 plots. So these are basically I have taken one representative plot from each of these different color regimes. Okay, so you see that this matches very nicely. Okay, and so one can also look at the large deviation function now, and you see that this greener, the large deviation function got analytically by taking delta going to 0. So this is the exact large deviation function in the limit delta going to 0. And these others are again the exact large deviation function computed numerically from the theory for different values of delta. And you see that actually as you take delta going to 0, it approaches this green curve in all of these regimes. Okay. So now let's just look at this function f of s and see whether it's a linear function or something else. Okay. So you see that this function, except these two cases, which are there are these two phase diagrams where we had these two yellow patches. So this is linear. In all other cases, this is okay, there's a linear part near 0, but it becomes something else. Okay. So therefore, in this kind of systems, okay, so your large division function basically, or symmetry of the large division function goes from linear to something else. Okay, and this is, I'm just showing the asymptotic, and you see that, okay, this asymptotic, so these green lines are the linear line, which says fs equal to s, and you see that these asymptotics are basically quite different from this fs equal to s. Okay, so what is the mechanism by which you get this? Okay, so it's a stochastic system. Okay, I can describe by this Lange equation, and so if you are interested in some entropy production, so let's look at the entropy production of the medium. Okay, so one can look at this generating function given the initial degrees of freedom and the final degrees of freedom. So where u is a short form for x and v, and it satisfies some kind of tilted Fokker-Planck equation. Right? This L lambda is the tilted Fokker-Planck operator. And at large time, so I need to look at I can decompose, I can write z as a function in terms of its eigenbasis, and at large time, what dominates is the largest eigenvalue. So basically, I need to find out the largest eigenvalue of this tilted operator, and this psi and chi, these are just the right and left eigenvectors. Okay, so I need to find basically this mu lambda, this and this, and so in this case, the quantities, this delta s, what we are looking at, these are quadratic quantities, quadratic functionals, and the system I have chosen, these are linear equations. So I'm looking at basically some quadratic functional of linear equations, and this we can solve it exactly to get this mu lambda and all these quantities, exactly in the sense in some integral form. And now, if you look at all these quantities, basically the generating function will have this form where this mu lambda is given by this. And if you are interested in the probability distribution function, you just invert it by saddle point. And this your I of s, which is the large division function, will be basically related to mu lambda by this saddle point equation, which is like the Legendre transform, basically. Okay. So now, if fluctuation theorem is valid, so that means that this quantity should have this one. And this 0 means that when this case where delta equal to 0, because we know that delta equal to 0 fluctuation theorem is valid, when A and B are completely uncoupled. So in that case, this I has this symmetry. So you can also see that in that case, this symmetry also implies that this largest eigenvalue, it should have something called Galois coherent symmetry, so which is given by this. And not only this eigenvalue, also this saddle point, in fact, should have this symmetry. So it's okay. It's like again a Galois coherent symmetry, basically. So all this should have this symmetry. So now, imagine that you have your mu lambda is something which is analytic. So this is the case in our case. So which is analytic in a given region, and of lambda, let's call it lambda minus and lambda plus, and it has these two branch points at these 2 points. Okay? So then when you compute the branch point, so branch point will always stay between lambda minus and lambda plus. Okay? And so that you can show. And so what you see that, okay, now mu lambda, so let's say I have a branch point here and here, and this, let's assume that these are my branch point behaviors. So as lambda goes to lambda plus, so it will have some value plus this branch point singularity. And similarly for lambda minus, it will have this singularity. And this branch point, the first term will also be related by this Galois-Cohen symmetry. Okay? So now, you want to compute the large S behavior. So you want to look at this function, what happened this function for large S. So you see that as S goes to infinity, so what happened this guy, so as S goes from minus infinity to plus infinity, this branch point moves from plus lambda to minus lambda. The branch point moves in the other direction. So now, as S goes to infinity, the dominant behavior basically comes from this branch point. And what you see is that basically, okay, so this is your branch point, so it becomes lambda minus, and when S goes to plus infinity, it becomes lambda plus. So therefore, your large deviation function, so it will have a term, when S goes to plus infinity, it should decay like lambda minus S. So lambda is a negative quantity. So similarly, as S goes to minus infinity, it should behave like lambda plus S. Okay? So now, so therefore, if you look at this, the difference I of S minus I of minus S, which was f of S. So immediately here, from here, you can see that these two guys are same because of Galois-Cohen symmetry. So they cancel. So it will have this one. So this lambda plus plus lambda minus is equal to 1 again because of this saddle point symmetry. And plus you have these subleading terms. But in this case, these subleading terms will be exactly 0. So they will cancel 1 by 1. This is again because of this Galois-Cohen symmetry. So in this case, what you see is that this IS minus I of minus S, which will be basically linear in S. It will be exactly S. Okay? So this is the case where there is no coupling. So now let's see what happens if there is a coupling. Okay? For non-zero coupling, okay, you will again have this two branch point. Okay? So let's, now this new branch point, let's call it lambda minus delta and lambda plus delta. And you have the similar form as S goes to plus infinity minus infinity, you analyze similarly, and you will see that this, your I of S will have this term, prefactor, which was these guys, plus this contribution coming from the branch point. Plus you have subleading terms. Okay? So therefore, for large S, so when you take this difference, so it's just this guy plus this subleading terms. So now, this object need not be 0 because there is no symmetry for this when delta is present. So it will have some non-zero value, and it will have something, this need not be unity. So it will have some slope which can be different from unity. And plus you can have subleading corrections. Okay? So this is for any general delta. Okay? So what I said, okay, so this is the case slope where delta equal to 0. So for any general delta, so you'll have a different slope, which was basically given by this one. And it will also have an intersect, which is basically given by this one. Okay? So this is what it will have. Now the question is what happened when you take this delta going to 0, this guy remains somewhere here, or it just goes in smoothly to the curve where delta is equal to 0. Right? So the same question is essentially whether these two branch points, the new branch point, these two branch points, if you take delta going to 0, whether they become the old branch points or they become some new branch points. Okay? So on general ground, of course, you can have these possibilities. So one is, of course, as you take this branch points, delta goes to 0. they go back to their old branch points. So this is when your fluctuation theorem will be satisfied. But there are other possibilities. Okay, one of them goes to the corresponding old branch point, but this other guy goes and becomes something else. Similarly here, and both of them become something else. Okay, and these three cases I was calling P1, P2, P2, P3, P4, and those are these three regions you have seen in that phase diagram. Okay, so now, so in that case, suppose you just look at this case 2. So we are now calling that, okay, this branch point goes and sticks somewhere there. And this is your new branch point. So you can in fact show that this branch point has to be on the right of the old branch point. So this is your new branch point. So now what will happen actually when your saddle point will be basically within this lambda minus tilde and lambda plus. You cannot access this old branch point. So it will basically move within that. So now if you want to analyze this thing here, so lambda, so you can break it into two parts. So one part which is analytic behavior when delta goes to 0, plus this part which is singular. Okay, so this has this branch point behavior. This analytic part when delta goes to 0, so that goes to the old analytic part for the delta equal to 0 case. But this new part, okay, this is some singular part, so which you expect that it should have this kind of form, okay, it has some branch point, but it should have a prefactor which goes to 0 if you put delta exactly equal to 0, right? Because I know that delta equal to 0, this term was not there. So it should have some prefactor, I mean, delta to the power something, it doesn't matter, but this guy should go to 0 as delta goes to 0. So it will have some this kind of form for small delta. So now if you analyze the saddle point for this case, so what you see is that, okay, this is your saddle point equation now. So this guy is coming from this part. So this is just this part. Plus this guy is coming from this new branch point part. And this is equal to minus s. So this is your saddle point equation. Right? So now, if you are somewhere there, suppose your branch point is somewhere, saddle point is somewhere here, which is very far from this one. So you can ignore this term because this term is very small in the limit delta going to 0. So you can actually cancel this term. So then what you have is that your this large deviation function is same as your old large deviation function. But at some point, your saddle point will come and it will come very close to this new branch point. And at some point, this guy will become dominant. This will become like a subdominant term. So in this case, so this becomes important and you have to compute a new saddle point solution from here. And this is what gives you the new saddle point. And then you can take this lambda going to 0. This subleading term goes away. And this is what you get this new saddle point solution. So therefore, corresponding to these four cases, you will have this. So you can compute this I of s corresponding to all these four cases. And similarly, you will have this f of s corresponding to all these four cases. And this is what you get. Okay, so let me just summarize that. Okay, so what we have shown that in some models, at least, or some situations, you can have this symmetry of this large deviation function, which is not equal to s but something else. Okay, so it's which we call it. Okay, it's like a basically even the limit coupling strength goes to 0, you can have a violation of fluctuation theorem. Okay. So this you can call a new fluctuation theorem, but okay, this is some name. I mean, what's there in a name? And then we have also so it also, okay, this finding says that, okay, if you want to find if your system is coupled to something else or not, this is one mechanism to find out. Basically, you just put this force on that and see your fluctuation theorem is satisfied or not. Okay. Okay. So this is the summary. Okay, so let me just so you can also say now that, okay, these are the free systems. So now if you put the system in a harmonic trap, so then you say that you see that delta going to 0 limit this fluctuation theorem actually satisfies. And the reason is that, so if you take this, if you put everything in the trap, so there is a time scale which is given by the trap. So in this case, what happens if the trap is not there, your coupling gives you a new time scale. And since you are looking at this large deviation problem, so at some point, basically, you will be basically above this time scale, and where although your system is not coupled, but for large entropy production, you have to go for very large separations, and that behaves like a coupled system. Okay, so that's why you have this breakdown of this fluctuation theorem there. But once you put it in a bath, what happens? It already has a time scale, and your new coupling basically changes the time scale by a small amount. So therefore, you do not see this in the limit when the coupling strength goes to 0, it basically goes back to your original problem. So this, in fact, you can see in terms of this. So if you have this mu lambda, so mu lambda has this form, and these guys have some quadratic this thing. So now you want to find out where is the branch points of mu lambda. Okay, so for that, basically, you want to look at when is this integral inside becomes imaginary. So that's what gives you these branch points. So that's the point where this, for a given u, you look at what is this lambda plus minus when this guy becomes 0, the argument of this. And if you plot as a function of u, so what you see is that, so this blue is for delta equal to 0 case. Now if you have a finite delta, what you see is that, so this guy comes here, this almost follows the blue, but then here it does something different. And now, so this is the case where, now if you take delta going to 0, so this curve will go to the blue curve, except there is a point sticking here. And earlier, this was your branch point on one side, now this will become your new branch point. But instead of that, suppose you had something like that, there's a possibility also this guy goes like that and behaves like that. It becomes the opposite one. So in this case, your branch point is here because that's like a farther away. So you have to look at the closest one. So this is your branch point. So in this case, basically, so branch points gets deviated by a small amount when you have a finite small delta, and when you take delta going to 0, it goes back to the original one. Okay, so this is the mechanism of basically branch point shifting to another branch point in the limit delta going to 0. Okay, yeah, so I'll stop here. Thank you very much. Yeah.
So you mean that the previous research only discussed the P1 case? This is a previous case.
Yeah, exactly. Yeah. Also, in these previous ones, like that, their systems were such that basically your mu lambda there's no branch point in some sense, because these are like a just singular, regular perturbation this thing. So if you just take it, so in what happened in previous case, if you take a small delta, instead of s, is just the slope deviates a little bit, and if you take delta going to 0, it just goes back to the old one, actually. Yeah.
Thank you.
Yeah.
So I have one. So
yeah.
So do I understand right that the physics is happening because these particles become very far apart?
This become very far apart, and because see, you are looking at this. Sorry. See, which are the trajectories contributing to this large entropy production? So these are the trajectories where this particle becomes very far apart. And in that case, this term, although delta is very small, the energy term becomes comparable, basically. And now you cannot no longer ignore this other particle. Now it's as if for those one, it's basically a strongly coupled system, and you are neglecting part of it.
So if I want to make a lot of heat flow between my particles, I should stretch the string like crazy.
Yeah, exactly. Yeah.
They suddenly start to see each other.
Yeah, exactly. Yeah.
Ah.
Yeah. And since it's a large deviation thing, basically what you are doing is, okay, that's why it comes on that large scale, because it's already divided by time, right? So this comes from very large as events, and large as events are where these particles are basically stretching very much. Yeah.
Any more? If not, then thanks again.
Okay, thank you.